problems to practice. And I know as soon as you saw them, you downloaded them and tried them right away.
Yes.
I did one of them.
Oh,
Did you have difficulty?
I had trouble with number 3. I could
All
not
right.
figure out how to track it.
All right, let's go on and should I do any of the ones beforehand? Like arc length along a straight line, you can just regularly use the old distance formula there, right? That's no problem. Don't even need to use our integral formula.
Actually,
And I think we did one very similar to number 2 in class. Maybe we even did number 2 in class last time. So I'm going to try to convince you that in our arc length formula in rectangular coordinates, we're not forced to use a dx integral. Everything we do with increments in x, we can do with a dy integral. So that was the point on number 3. Our arc length formula in rectangular coordinates look like an integral from x is a to x is b. And under here, we have a square root of 1 plus f prime of x, all squared dx. But there's nothing magical about that being f prime of x. When we derived this formula, we had the change of x squared here and the change of y squared there. And I divided everything by a change of x to get that out here. But had I divided by a change in y, we could have also written the arc length formula as a function of y. And so we would have a 1 plus the derivative of f as a function of y and a dy here. So this we denoted as dy dx all squared, and this we denoted as dx dy all squared. But here x is a function of y, and here y is a function of x.
yeah, so do we need a squared there?
And a squared, yes, thank you.
You get the same answer.
You will get the same answer. So maybe we'll try number 3 both ways, as a function of x and as a function of y, and we'll be stunned and amazed when we get the same answer. And one way might be easier than the other. So my example on number 3 was we've got the graph of 12xy is equal to 4y to the 4th plus 3. Now I've already changed my mind about trying this as y as a function of x. If I want y as a function of x, I've got a nonlinear equation to solve to get the y by itself, and I don't think I can do that. Right? I would have to use some version of the quadratic formula twice. Sign me out again. Okay, fine, be that way.
Are you recording?
I think so.
Okay, just want to make
Sure.
sure.
So I've got a red dot in my cloud. It tickles, but I got a red dot in my cloud. What does that mean? So I can't do it this way because there's no way I can get the y by itself. I get y in terms of x and y, but I can't get the y all by itself. But I can get x by itself. First thing I'm going to do is divide by y. Okay, let's go ahead and divide by the 12 as well. Why am I leaving that 12 behind? Let's divide by 12y. I know eventually I'm going to need a y prime. I'm not so fond of doing the quotient rule, so since I just have a single term here, I'm going to divide that up into 2 fractions. So let's write x is equal to 4y to the 4th over 12y plus 3 over 12y, and simplify that. So that first term simplifies to 1/3 y cubed. And the other one simplifies to 1/4 y to the -1. And I wrote it as y to the -1 so I could take the derivative in the next step. So now we're going to do this. We're going to find the derivative of that x where y is the independent variable. So the derivative of x with respect to y, let's see, that's just gonna give me just a y squared once the 3's cancel. And this one will give me minus 1/4 y to the negative 2. Then we had an ordered pair. I didn't write that down. I'm gonna need my ordered pairs. We want the arc length from point A, 7/12 to point B, 67/24 to the point 2. And already the y's look better than the x's, don't they? So let's put it all in here and see if we can do that integral. So the integral that we're going to do is S is equal to the integral on the range of y's from y is 1 to y is 2 of the square root of 1 plus that derivative over there, y squared minus 1/4 y to the negative 2, all squared, and dy. Way to make that focus. Let's see how to make it focus. It just looks so blurry.
Sure it's not your glasses.
It could be. I should pay more than $5 for glasses, huh? All right, let's square this. Now, let's do it right here. I'm going to take y squared minus 1/4 y to the negative 2 and multiply it with itself. So that times that gives me y to the 4th. Run out of places in which I can put this. I'm going to put it right here.
I don't think I've ever multiplied y squared to y to the negative 2.
And how do you multiply, say, an x squared with an x to the 5th?
You add the add them.
Yeah, the exponents.
You just get a 0.
So you get a y to the 0, which means what?
It's just interesting that I've never done that before.
All right, so that times that just gives us a negative 1/4, right? So here's the 1 from the formula. Here's the y to the 4th from squaring. And our middle terms are both going to give us
1/2 total.
a negative 1/4, negative 1/4 plus another negative 1/4 gives us negative 1/2. And then what's the last term going to be?
1/16 y to the negative 4.
Positive 1/16.
And then we got the dy here. Are you with me there? And then we can put these two together. And I'm going to get a plus 1/2 in the middle. Can you integrate that?
Oh, we have to
Square root.
change it into the original polynomial, but change the sign.
Right. As it sits, we can't integrate it because we would have to do a UDU substitution. But I told you to look out. These problems are set up so that when you simplify, you should get something that's a perfect square. And this looks almost exactly to this, which came from multiplying that out with the minus sign in between. If I change this to a plus sign, I should get a plus 1/2 in the middle here. So this should factor as y squared plus 1/4 y to the negative 2 all squared. Okay, so you're looking for that. You're warned by somebody older and wiser than you that this should be a perfect square, and it is. So now we're left to integrate 1 to 2, the square root. What did I say that factored as? Y squared plus 1/4 y to the negative 2 quantity squared. And that was what we needed. so that I can now take the square root of a quantity squared and get that stuff in the parentheses all by itself. We got y squared plus 1/4 y to the -2 without a square root now, dy. So that was the magic. That's what you had to be on your toes for. Not really magic, it's algebra. Right with me? So now we integrate and we get y cubed over 3. And this becomes minus 1/4 y to the -1. Evaluate from 1 to 2. Y to the -1 means 1 over y. And so here I'll get 8/3 minus 1 over 2 to the -1, which is a half, times a fourth is an eighth. 1 to any power is 1, so I get 1/3 minus 1/4. So I have 8/3 minus 1/3 is 7/3 minus 1/8 plus 1/4. Where I come from, that's good enough. Okay. Everybody? So the same kind of deal should have happened on number 2. So let's do the polar curves. I think we did a version of number 4 already. We did a sine last time, right? We can probably do a cosine. So let's look at number 5, the spiral. The polar coordinates version of this formula didn't have the 1 under the square root, instead it had an r. So in polar coordinates, for r is some function of theta, arc length look like an integral. These numbers are from theta is equal to a to theta is equal to b. The square root sign had an r squared added to a derivative, dr d theta squared. So the example that I have there is example 5. I want to find the length of r is equal to 2 to the theta for theta between 0 and 2 pi. And I said that that was a spiral, right? So it starts out at 2 to the 0. 2 to the 0 is 1. So what? 2 to the 0 is 1. And then 2 to the pi halves is 1-ish. And then 2, then we're going to get bigger and bigger as we go around. It's going to be some version of this. 2 to the 2 pi, something like that. So we're going to find the length around that. All right, so we take the derivative of that. How do you take the derivative of theta?
It's just the same as like a
Times the
constant to the
natural
x.
Remember the derivative of 2 to the x?
Oh, yeah, I did it earlier. I forgot.
It's just like the derivative of e to the x. What's the derivative of e to the x?
E to the x.
The derivative of 2 to the x is 2 to the x, except now we have to compensate for the fact that 2 is not base e, and multiply it by the natural log of 2. We can say that 2 to the theta is the same as 2, I'm sorry, e to the natural log of 2 to the theta, agree? Because e to the natural log of anything is that anything?
Yes.
And then that log power brings the theta down. Natural log of 2 is just a constant. And so if I want to take the derivative with respect to theta of 2 to the theta, I just take the derivative of that. The derivative of e to any power is itself times the derivative of the exponent. Natural log of 2 is a constant, theta is the variable. Derivative of theta is 1, so I get 1 times the natural log of 2. This was equivalent to 2 to the theta. So there's the derivative of 2 to the theta itself times the natural log of 2.
Could you use like the power rule and set the exponent as like theta times 2 to the power of theta minus 1?
No, because that power rule only applies when the exponent is a constant, not when it's a. So there's my derivative. That's going to go in that second slot after I square it. But I have to square r itself in the first slot. So in this problem, I'm given the numbers to put here. Then I've got to take my r and square it. Then I take my derivative and square it and integrate that as a function of theta. So what's the square of 2 to the theta? 2 to the 2 theta? So when I square that, I get another 2 to the 2 theta. And then I get a natural log of 2 all squared. So I can't integrate it as a sum. So I'm going to try to do is simplify this a little bit. I see a common factor of 2 to the 2 theta. Under the radical sign, I'm going to factor that out. And that's going to leave me a 1 in this slot, a natural log of 2 all squared in the second slot. If you have a product, then you could take the square root of the product by taking the square root of the first term times the square root of the second term. What's the square root of 2 to the 2 theta? 2 theta, 2 to the 1 theta. There's that. That's a constant. So I'm going to take it out front. Oh, now we've got to integrate that. So to integrate that, let's write it like this and do a u to u substitution. 2 to the 2 theta is equivalent to this. So we'll write it as e to the natural log of 2 and integrate that. So we'll take u to be the power. Oops. Theta natural log of 2, I wrote that backwards. U is theta natural log of 2, then du is the natural log of 2 times d theta. So du divided by the natural log of 2 is the d theta. So I'm going to write that now as e to the u times du over the natural log of 2. The natural log of 2 is a constant, so I'm going to put it underneath this. So now I'm integrating e to the u du. What's the integral of e to the u? E to the u. So we're just about done. I get e to the u here. Let's go ahead and replace u again. U is e to the theta natural log of 2, and we evaluate that from 0 to 2 pi. But remember, this number, if you like, is 2 to the theta. So I'm going to have 2 to the 2 pi minus 2 to the 0. 2 to the 2 pi is just 2 to the 2 pi. 2 to the 0 is 1. So here's our answer. Arc length is the square root of 1 plus the natural log of 2 all squared divided by the natural log of 2. Then I have 2 to the 2 pi minus 1 times that. Believe it or not, that's a positive number.
I believe you.
You believe me?
I believe you.
It's probably nobody's favorite number.
It's not mine.
Is that like somebody's constant?
It's not a
It's
constant.
Jack's constant.
You want it, you got it.
I'll take it.
So sometimes using these formulas takes a little bit of scratching around in memory junk. Algebra in terms of rectangular coordinates. Pythagorean theorem, one of the ones on your web work is f of theta is a sine theta minus a cosine theta. Maybe you got to do a lot of squaring of that. So it's kind of an easy formula to remember, but using it takes a little bit of practice. So I hope that you have time in your life to practice this. No?
Not this week, next week I do.
I do.
Good. Everybody okay? Do you have anything you want to ask about any web works? Anything you want to ask me about what's going on in your web?
I don't.
problems? No? Nothing? You want me to start the next section?
Just making sure there was.
Is that what you're telling me?
No.
No?
I'm not.
You want me to stare at you? You're gonna ask me a question?
Need more practice.
Need more practice. Everybody needs more practice. Yes, sir.
6.4 web work didn't show up on my page. I didn't know
It's not open?
Yeah, it's not open.
It's supposed to be.
Extension.
Tell me that now.
I didn't know it was supposed to.
Yeah, we just thought we were getting lucky.
No. What? I just wanted.
Save it. We have the class to work on it. Now.
Oh, let's see what's wrong with that.
We probably all need it just for the sake of our grade.
I think I know. I thought she was
We
just.
got 10 days. We can.
That's what I thought. I thought she was gonna.
And tomorrow's already cut off.
No, this is so relaxing.
It's not both.
Radiant mode.
They're going to do it. When they come
Almost
to
every day,
it,
so
really
it's like a
quick.
7 foot, so you stand up
Oh, nice.
on a stage.
I have a quiz in one of my
Oh,
classes.
is that
It
good?
literally opens Friday
Does he
at
keep going
5
all the way
and
till
it
6?
closes Monday.
He starts at 3:30.
So you literally
Oh,
assigned
mine's
a
probably already started.
weekend quiz. That's so fun. Let's hope it's Friday. Like,
Which is
we're
what
just
you see
going
that
to
the
Mine opens at 2.
It's not gonna open until October, August 22nd in the year 2030.
Yeah, we'll get that to you in the next decade.
I'll be dead in 2030.
Oh my
I wrote that on my grave.
Is that a wish or a
Instead of
sarcasm?
flowers, we'll bring you.
We'll make sure to carve
Every single.
we'll like
formula into your
origami the
grade.
math homework in shape of flowers.
Oh, let's edit that. Let me see if I even made it yet.
Oh, Riley says you haven't started the Zoom yet.
It's got a dot up there.
It's recording.
He's recording, but it's not like. Or he's letting not. you
I gotta
edit.
share.
It's not open.
Share screen, huh? Sorry, we didn't miss anything exciting. Where's my share screen?
They just see that on the board.
They see that and they're like, well.
Wait.
Yeah, that's always scary to approach.
Yeah. I'm still.
It's not so scary when you know you're doing
Right.
it, but it's just scary to like walk up and.
But he's gone from my Zoom.
Really,
I just told him to get back in.
Okay. I screwed that up, huh? But it was recording, so that part will be on the record. Good to see you.
That's what.
Okay, guys.
All right, let's make this.
Anything raised?
Today is not 2030.
Because then we can just substitute exponent.
It is 9:10.
Well, 2 is close enough to E. I mean, they both start with 2.
Yeah.
So in the grand scheme of numbers, in the grand scheme of infinity, then
If we just change it into E and don't worry about it.
It's close enough. I mean, I have a month to gain.
I would raise it more.
I would round it. More than like 300. I'm considering not rounding it, but. Being
What is this? Why did you do that, Jay?
Well, you have to pick how 3 works, right?
Like, hold up. I'm 3 late,
Well, you have to calculate the length of the pipe that's in the wall, but instead of just going straight down the wall. You have to go around like
Then
3
you have
electrical
to-
boxes and.
Yeah, if
you
the
have to
electrician and the
make it
plumber didn't
work.
work together. So that they now have to understand calculus because they don't know how to work.
You know what?
Somebody who can.
I think
You accept it.
You
could just beg.
3 dimensions.
Evidently, those guys make like $100 a day, so like the people that beg on the streets.
Yeah. I think I'm thinking. I'm gonna drive the old truck.
You have to do that.
Do trade school or something? And if you can get an apprenticeship right now, you don't have to.
How many things would you weld do?
So should I make this due this afternoon?
All of it.
I don't have 2 lanes wide.
When was it supposed to be due? Like Sunday?
No, like today.
Really?
Super big.
Yesterday.
Before the super duper.
Yeah, last night. You wouldn't do that to us.
All right, y'all.
Don't.
We have an exam, so it's after 10. We don't want it the day before. All right, let's move back to the exam.
Yeah, I wouldn't have made it.
Yeah, like next
I'm just
Friday.
gonna weld an
would be
engine
good.
to it that's not like attached to anything and just running.
I'll just make it. That way you get the weekend to study for the exam.
Yeah, let's do it. Sit down here.
Since we're supposed to be
That's
doing chapter
easy,
two.
that's easy, that's
Whatever.
easy.
Chapter one.
Arc length,
I was
arc
like,
length.
is this gonna be all the test? I was like, no, why would you?
I'm so scared.
Curve. I don't want a surface integral. I need some polar things on here.
So I was like.
Do we though?
Because.
Yeah,
sometimes I
you know what?
lecture you
I'm
say,
gonna
I just
think you
don't
should
feel
just,
like
instead of adding anything, but I do
Replace
think.
the stuff that's
So-
already there.
you
Okay, that is
wonder
because
why
I'm forgetting.
you put something-
Yeah. What if you just like.
The lever,
It's
it's
like
fine.
one problem.
It's fine. I work inside.
But it's like super short. You have one problem, but it's hard to say through it. No. It's one problem and it's.
Because like,
no
at least
outlet.
like this.
There's no outlet.
No, don't do that. That's why.
There's just 85 blanks.
Yeah, last semester.
You have to, it's a combination. You gotta guess the combination.
Well, you start writing every number and then the ones that you get right.
Like,
You
it's a really-
change the ones that. They doesn't tell you.
Oh, shoot.
I'll have to fix this later. There's not any good ones on here. I'll get that open for you.
When do you think
Well,
it'll
a
be?
lot of it is like, what is
I guess
this?
in about a week, huh?
That sounds about right.
That's pretty tough. Just before the.
Okay, so it's not like
My-
your beliefs, it's someone else,
my-
yes, okay.
But you
1 to 2 days after.
No.
Why don't we just move it away from that?
Might have studied your SATs going on.
Huh?
Have you ever studied after the exam?
Yeah, that is.
No, I have.
Well, yeah, to study for the next.
No, I'm talking about like studying the content that you took in the exam after. you took the exam.
Still in English, but you study 4 hours.
So,
Yeah,
I've done that.
honors, like, if-
I've done that before.
I've like these tests, but I did wrong. I literally had to flip my answers for like a month. Upside down. So now I'm in Cal too.
And you haven't taken Cal one?
No, I've taken Cal.
Oh,
I took it in high school. College.
I mean, I took Cal 1 3 years ago.
Because these are actually like.
So how do you do it now?
We have like 4 cents.
All the picture.
That's a painful file.
I was like, I forgot how to take it.
Yeah, well, I forgot how to do the river.
How do I get this to take my own screen again?
I remember the basic.
The final is
Specific.
really
I don't remember the inverse.
I think it is.
Oh, I forgot all
You don't know
of
the
them.
arcs? I don't know the arcs.
If you did.
Who doesn't know the arcs?
She's like.
Why is this showing just so little? What's going on here?
You're sharing your whole
Make
screen.
that big.
You didn't need to share.
Oh,
We need a
So go to the very, very bottom where you see the Zoom logo and maybe click that all the way and it will pull up the full window. Yeah, and then click the,
No, just stop sharing your screen.
Stop sharing my screen.
Oh, that's what it is.
That
You're
was the
sharing,
problem.
you're sharing your entire screen and not just the
I thought he
camera.
wasn't seeing it at home.
no, he wasn't, he
not in
wasn't there.
I'm not there now.
In the Zoom, that's why he couldn't see.
He's like, oh, it's not happening.
I thought the problem was he couldn't connect to the Zoom meeting.
Yeah.
Couldn't connect.
Was that correct?
It's still recording though, so we're all good.
Okay,
It's that guy.
what? A glitch in my recording? That never happens.
That does not work.
It's because I turned off the projector too late, wasn't it?
No, it's because she didn't set a timer.
Well, she did set a timer. You didn't? I told you to.
You had one job.
I told you to, like.
I know, but I remember her yelling on.
Okay.
You can start the timer. That doesn't ever work.
Cause the disturbance in space.
You know, there's some people that have to like wake up when they want to.
Yes.
Like, I had that.
What I do on Saturday is totally not up to me. I just follow everybody around.
Like an hour early. And I'll say, okay, I don't know, I'll go back to.
You have to meet him personally.
I'd love to. You can have, I'd love to.
Yeah, take a picture with him. He's like, and then show us.
Sometimes these people that come are divas.
Really?
They only do what their contract says. Okay, so you'll have some arc length problems to practice eventually, but I am going to move on. The next section is another application of a definite integral applied to work.
Work.
How many of you are in physics? How do you define work in physics? Force times distance. In other words, work is measurable if you can apply a force to an object that causes that object to move a certain distance. So if I get up here and apply a force to this wall,
Not doing
as
it.
hard as I can, it didn't move. It actually
You
didn't.
did do work though, because your
I did
muscles.
no work.
No, you did work because your muscles moved.
Not on this
Your muscles
floor.
moved. though.
My muscles quit moving years ago. But if I can't make it move, then there's no work done. Force times distance, right? But now if I have, for instance, a 20-pound bag of potatoes sitting on the floor, and I take that 20-pound bag of potatoes and I put it up here on a table at a height of 4 feet, I've done some work. How much? That's pounds and feet. 20 pounds of potatoes, moved a distance of 4 feet. I've done a total of force is my 20 pounds times the distance, 4 feet. So I've done 80 foot-pounds of work right there. So if the object has a constant mass, weight,
It's weight for.
Weight.
Pounds.
because weight, it's in pounds, and moved a fixed distance, then work is just the product. So section 6.5.
Hey, we're gonna have 10 days to go through the entire.
And so work
So really.
on an object is done by applying a force that causes the object to move a certain distance. And so that work is just the product, force times the distance.
Are we about to get into dot and cross products? Or is that like
Because
purely,
we're not gonna do this in vector style, you'll do that in
is that just?
Cal 3.
Oh, okay.
We'll do work in Cal 3 with vectors.
Man, my physics teacher was crazy.
He had us all the way up to Cal 3.
Yeah.
Holy cow.
So in this definition, force is constant. Because my bag of potatoes didn't change its size or shape as I moved it. But if maybe it was a leaking bucket of water instead of a bag of potatoes, then it's a different force applied to it as water has left the object. So I have to think of how to do something like that. Or maybe I've got a chain that I'm moving. There's a chain laying on there and I have to pull the chain up one rung at a time and lay it on here. So as some's here, less of it's there. So it takes less of a force as I've moved already some of it up here. And so if the force is not a constant, that's where the calculus comes into play. If I've got an object, let's move it along a number line. And the force is not going to be constant, it's going to depend on where I am on the number line. Then I take my number line and I cut it up into itty bitty teeny tiny intervals so that over that tiny interval, the force is a constant. So I take the force on that tiny interval and move it across that tiny interval. And then I find the work done on that tiny interval. I do it again and again and again, and I add them up. And I make a Riemann sum out of it by making the size of the intervals go to 0. So if force is not constant, say the force is some function of x on a number line. Say here's my number line, and I need to go from x is equal to a over to x is equal to b with whatever my object is. I cut this up into tiny intervals of with delta x. And so that would be the kth subinterval. So the force is going to be F acting on x in that kth subinterval. And so the work done in the kth subinterval, or let's even call it, that's work done in the kth subinterval, or just how much work is done in the kth subinterval, is the product of that force times that distance. So to get the total work is the sum of these. So the total work is the Riemann sum. K is equal to 1 to n. I'm going to have to squeeze a limit in there, so I'm going to move that over, of the force on the kth component times that width. Now we squeeze in that limit. As the size of the subinterval gets small, we're making an infinite number of subintervals. And we've seen that this becomes a definite integral then, that has the same shape as that. Going from x is a to x is b, the force is a variable function integrated with respect to x. Let's get some units together here. Units. So if we have force is measured in pounds and distance in feet, then the units of work are foot-pounds. If we go to the metric units of measurement, and maybe our weight of the object is in kilograms, and we move some certain amount of kilograms, then the force applied to the kilograms would be measured in newtons. So if mass of the object is in kilograms, then force is in newtons. And then distance is in meters. And work would then be Newton meters, but nobody calls them Newton meters. What are Newton meters called?
Joules.
Joules. Work is in joules. Okay, so Newton's meters are called joules. If we're moving something tiny, so we're moving things maybe in units of centimeters instead of meters, and
That would just be a centijole.
if mass is real small, grams instead of kilograms, and distance is in centimeters, if mass is in grams and distance in centimeters, then force is in dynes, is that correct? Yep, dynes. And work is in, so to be dynes centimeters, my favorite work measurement of all. It's called an erg.
Ooh.
Erg,
I feel like that would be better for the heavier one.
you know. Erg.
The things a physics teacher glosses over.
In math, we don't do units.
I've learned more physics in math than I have in physics.
Do you know that sometimes mass is measured in slugs?
Yeah.
That's here.
Yeah, that's what.
Here, mass is in slugs.
And stone.
That's in our pounds and feet. We measure mass in slugs.
Who is in charge of these names? I want to know.
Here, I'm thinking it was old Isaac himself and his buddy Jim Bob Jewell.
I mean, when they measure weight in stone and stuff like that, you know,
Like
it's the British.
That makes
That's
sense.
British, because they were
Yeah.
weird.
The British are
right?
weird.
Yes.
Wasn't
And then we're talking about feet, and that's
I-
literally feet.
I heard that you said were weird. I think.
Oh,
are.
yeah. Okay, so I often have to look up units because I'm a foot pounds kind of gal. Even though I like to slip an erg in there every now and then. But your units are going to be important in your physics classes. And a lot of times on WebWork, it says enter your appropriate units. Okay, now, well, good morning.
No, he's.
Wait a minute,
That's all
last
for
time you
today.
said it'll never happen again.
I know, I had put several alarms up. and
Today
it's-
is never.
I really hope he's up to date.
Okay, so if we have just the constant things, pick the bag of potatoes up, 20-pound bag, 4 feet, then 4 times 20 gives us 80 foot-pounds of work. But if we have to chop things up into little bitty slices, then we got to make an integral out of it. So I'm going to take an example where I'm going to take a 50-foot long cable and I'm going to wind it up, find the work done in winding it up. All right, so I sent these to you so you wouldn't have to write them all down. If you opened your email, they're in there and you don't have to write them all down. If you didn't open that, here it is. Cable is 50 meters long and has a density of 3 kilograms per meter. We're going to find the work done in winding the cable all the way up in a little thingamabobber.
Cool.
This says a winch. But I was kind of offended by that word.
Yeah.
I think I've been called winch before. Maybe not winch.
It's like a pirate edition class or something.
Ergs.
They're using ergs and they,
Find the
is
word.
that where you learned about ergs?
Find the
Isn't
word.
International Speak of Pirate Day coming up?
Okay, let me ask you physics people. There are 2 different kinds of densities. There's a weight density and a mass density. What's the difference?
One goes off weight, one goes off mass.
What does that mean?
One is heavily affected by gravity.
One has the gravitational constant already included in it, right? What is the, if you're in meters, what is the constant force of gravity?
Negative 9.8.
9.8. And if you're in
Engineer.
feet, it's something like
16, right?
I don't know.
32.
That's like, yeah, that's like
32 feet per second per second. When we're talking density here, we're going to assume that the gravitational constant is already in here.
Also, we're finding the word and not the work.
Happens.
Find the word done in winding the cable. It's erg.
Where
That's
is
why
the
my
word
hands
done?
look like
I couldn't
that.
find it.
There's no.
Find the word, there it is.
Where is the word done?
Just, you have all the letters with you.
Okay, so here's what we're going to do. I'm going to take my y-axis and I've got a 50-meter long cable. There's my cable. And I'm gonna, well, let's just make it look like a chain. As I wind it up, there's less and less and less and less and less there. So it all varies about which piece that I'm looking at. So I'm going to cut this up in an infinite number of thin pieces. So let's look at this piece whose width is delta y. So I have delta y feet of cable. What is the expressions for the force acting here and the distance acting here?
Why are we using feet instead of meters?
I've got meters, because I needed some red ink on my black hands.
Ah.
Delta y meters of cable. If it's 3 kilograms per meter, and I have delta y meters, how many kilograms of force do I have acting on that little tiny interval? 3 delta y. So our force on that interval is going to be 3 times delta y kilograms. Because this is kilograms per meter multiplied with meters of delta y. So that cancels and it gives me kilograms of force. So on that small interval, force is essentially constant.
Why is it kilogram to multiply
Yeah,
by the
it should be-
gravitational?
Gosh darn it.
So we need to multiply by 10?
Why can't I have kilograms?
Use kilograms is not force.
Yeah, it's a mass, right?
No, what did I just write up here and I erased?
Well, newtons is force.
Okay, forget it.
So we
I
can put
won't
our
wait. I'm not gonna put the 9.8 in here.
It's 3 kilograms times the delta Y meters, so it's gonna end up being kilogram meters.
So I'm gonna do my force in kilograms. Well, newtons.
Should file a
Just make it 30 delta Y.
You should file a complaint.
No,
with the
I'm gonna
metric
leave it
system.
with kilograms.
Please.
Okay.
I don't
Unless you'd like
care
to
about
do it.
these. Units aren't important. I want some sort of weight measurement. So there, grams,
okay.
kilograms, noodle grams, I don't care.
Slugs.
Loves. The important part is my force is a constant over that tiny interval. Now I've got to take that and move it from its location on the y-axis at some arbitrary y coordinate, somewhere between 0 and 50. And I need to move it from where it is to where it's going to be. So what's the distance that that little tiny piece of cable has to move?
50
Delta Y.
No,
Minus
the
y.
delta y is the width.
Oh, shoot.
50 minus y is the distance it has to move. Some y value in that, on that number line.
I think that's supposed to be 50.
That is a 50.
There's a 50.
So the total work on that interval is the force on that interval times the distance on that interval. So I'm going to have my 3 delta y. So that's kilograms, that's meters. And so now when I multiply them together, I have my units of work of kilogram meters. And now we're going to add them up with a definite integral. So the overall work now becomes black instead of red. The overall work is going to be a definite integral. The delta y becomes our dy. And then these guys become the part of the definite integral. Then I'm going to cut up my number line from y is equal to 0 up to y is equal to 50. And so that's kind of an easy integral to do. We just multiply that out and I get 150 minus 3y that I need to integrate. We take it up here and we get 150 y minus 3y squared over 2 from 0 to 50. I don't know what 150 times 50 is.
7,500. Yeah,
How much?
7,500.
I think the final answer
Now we
is
get 50 squared.
it's 3,700.
That's 20.
2,500.
About that.
2,500 divided by 2.
No,
Times
it's times 3, so.
Yeah, well, 20.
Oh, I forgot. I did 2,500 times 3 divided by 2. So I take them away from 2 over 2 and I get that over 2. And that's already too much division.
3,750.
Yeah,
And so this would be in units of hopefully joules, give or take my kilogram stuff.
joules over 10.
Joules over 10.
Well, you can just take it as 0 then. Just erase the 0.
We don't do gravity in this classroom, Jack.
Well, actually,
I expect you to learn and float away by.
Actually, we do gravity.
Unit 16. I expect you to master.
One of the things in mechanical engineering that is often used is stretching and contracting a spring, not even in physics. Because springs follow something called Hooke's law.
Store energy.
What does Hooke's law say?
The spring
The-
constant
The
times
spring has a
distance.
constant stretching force.
Yeah, springs are easy because Hooke's law says that the force required to displace a spring from its natural length to a distance beyond its natural length, that force is directly proportional to the distance that you're stretching it. The force required to stretch a spring beyond its natural length is directly proportional to that distance that it's stretched beyond its natural length. So let me write that down. To a certain point until it snaps.
Yes.
Don't put all these details in here. I just want calculus.
We don't want to like actually do things the way they're intended. We want
I'm
to
gonna give you the
theoretical.
Reader's Digest version, and then when you're in your physics and engineering
Doing
classes,
it all wrong.
they're gonna get my rough edges and make them nice and smooth for you.
Sounds good to me.
why towers collapse.
Probably.
And that is not at all what I meant by anything.
That was like,
Yeah.
If y'all wanna see it,
based on
we're
time sensitivity.
we're one day away, Jeff.
Yeah, that's not what I meant. I was just thinking like a general building. Yeah.
More time.
I'm gonna take.
Yeah.
It's
It's recorded.
you're a little too close.
Yeah, it has been recorded. I'm sorry, camera.
Hooke's law states that the force required to stretch or even compress. Correct. Is that spelled right?
Yeah.
A spring. Certain distance. Beyond its natural length. Is directly proportional to that distance. That took a long time to write something that's very, very easy. If this is the natural length of a spring, and then you're going to stretch it X units beyond the natural length. So we're going to stretch that string X units beyond its natural length, then F is roughly equal to X. Roughly equal to, there's going to be some constant of proportionality, a constant. Force is some constant times this distance. Each spring has its own constant, called the spring constant. And so if that's the force, and I want to compute work done in stretching the spring, there has been some displacement. It varies, it's variable, right? It depends on X. So that will be cut up in little dx intervals. And my work then can be written as a definite integral of the force times the distance, dx. And so our work is going to be force times our distance, which is k times x times dx. And this, the part that's being cut up is the part that's being moved. So that's going to be distance beyond the natural length. So the numbers here represent natural length corresponds to x is 0. to whatever x is. So this represents the displacement beyond natural length. Let's see if we can do one of these. Suppose a force of 3 pounds is required to hold a spring that has been stretched 1/4 foot from its natural length. Before we find work, that sentence is enough in order to find the spring constant. After we find the spring constant, then let's find the work done in stretching the spring 6 inches beyond its natural length.
Oh, we just use like 12 and stuff like that.
12 and stuff like that.
These are feet.
Yeah, I'll have to change inches to feet. I'll do that.
Please, please.
No, just leave it.
I've always been a fan of imperial units, but sometimes they hurt me.
Yeah. So how did I know right there that I could write in blue that you could find the spring constant from the sentence above?
Because we have a force and a distance.
Because it's a simple little equation with 3 parts. 1, 2, 3, I gave you 2 of the 3 parts. I gave you the force, I gave you the distance, and asked you to find K. Right there in blue, let's kind of put that in. The force is 3 pounds. K is what we're looking for, and then 1/4 foot. So to multiply both sides by 4, we got K is 12. There's the spring constant. So now I know that force throughout this entire problem as a function of distance beyond natural length is K times X. Now we can do the second part. Find the work done in stretching the spring 1/2 foot beyond its natural length. We want to make our units agree. Our work units are going to be in foot pounds, so convert that to 1/2 foot. Well, this says the work done, this says it's gone. The work done should be just the integral of the force times dx over the distance beyond its natural length. So work is the integral of f of x dx. So it's k, which is 12 times x dx. We're going to go from its natural length to 1/2 foot beyond. 6 inches is the 1/2 foot. Take it 6 inches beyond its natural length. So it's the easiest integral of all integrals we've done. So when I put the half in there and square it, I get 6/4, which is 3/2 units of work. We're in feet and pounds, so they're just foot-pounds of work.
Is it gonna get harder?
Sometimes they give you the work done and you're asked to find the spring constant. If you know how much work is done, can you find the spring constant?
Yeah.
Well, let's see, let me grab one out of the book here. 'Cause I didn't put one on this little handout. Let me grab one out of the book and see if you can tell the difference.
So we start using derivatives there.
No, even easier than that. Where did I have my problem? So this next example. The natural length of a certain spring is 10 centimeters.
This is gonna be hers.
Yeah. I gotta
Just
squeeze my
for
erg.
you.
Need a darker pen. Certain spring is, oh God, that's not darker. 10 centimeters. It requires 2 ergs of work to stretch the spring to a total length of 18 centimeters. I need a darker pen. Where's that blue? That was blue. A total length of 18 centimeters. So here's where we take the time out and find the spring constant from that information.
So that's 2 equals constant times 8.
And then once we find the spring constant, let's find the work done in stretching the spring to a total length of 20 centimeters. Let's say from stretching the spring from a length of 18 centimeters to a length of 20 centimeters. Here's the diagram. The natural length of the spring is 10 centimeters. That's its natural length. Then 2 ergs of work get it to 18 centimeters. Get it from here to here. And then I want to know how much work gets it from here to here. So this is in units of centimeters. But this is going to correspond to X is 0. Right, the natural length. Haven't done any stretching. So this one's going to correspond to X is 8. In Hooke's law, force is directly proportional to distance beyond the natural length. And this is going to correspond to X is 10. But nowhere in here did I talk about force. Everything in here talks about work. So I don't use F is Kx, I use work is the integral of K times X. So I'm going to write that the work is the integral of K times X and see if I can figure out what K is. Because I gave you 2 as work, and I gave you the numbers that go on the integral sign. So to get K, we start here. So we've got, so we start here. Work is equal to Kx dx. So in our problem, work was 2. K we don't know. But I went from its natural length to 18 centimeters, which was 8 units beyond its natural length. So I went from 0 centimeters beyond natural length to 8. We're going to solve that equation for K. So I integrate Kx and get Kx squared over 2. Evaluate that from 0 to 8. 8 squared is 64. 64 divided by 2 is 32. So I get 32K over here is equal to 2. So K is going to be 2 over 32 or 1 over 16. Now that we have the spring constant, we're going to find the work done on this tiny interval here. So it's work, so I got to set up an interval again. So from 18 centimeters to 20 centimeters, I've got work that's going to look like, well, 18 corresponded to 8 units beyond its natural length. The 20 takes me to 10 units beyond its natural length.
And we can just make that.
And then I have K times X dx.
Because the force would be different.
You sure?
Yes. Yes.
Oh, yeah, you're right. Okay.
Are you with me? So again, it's an easy integral. You just had to know that you started with work and not with F is K times X. Just read the problem. It tells you what you got. And so we finish the integration. We get X squared over 2. 2 times 16 is 32. And then evaluate that from 8 to 10. So I have 1 over 32 times 100 minus 64. 100 minus 64 is 36. 36 divided by 32. 9/8. I have 9/8 units of work.
9/8.
9/8 units of work to get it from 18 centimeters to 20 centimeters. Okay. Okay, so we've done moving pieces of chain. We've done stretching spring. Next time, we're going to talk about pumping water from a tank, pumping a liquid from a tank. So this section can get pretty long. It'll probably take all of next week doing most of this. I'll get you a web workup immediately. When I get back to my office.
I now have 12 hours.